Hey guys, coming in to do the second part of the class notes for the 6.7 FTC and the definite integrals. So as we saw in the last set of notes, that there is a direct relationship here in this turquoise highlight up there, a direct relationship to the definite integral from 2 to 5 and using the antiderivative, actually any antiderivative, and calculating the net change or the displacement. So what we're going to do here is we're going to come down and we're going to look at finding Nadine's actual position function, the one that is specific to where she was at 2 seconds in, where she was at 12. So coming down here to the bottom, sorry, get that off. All right, so, and hopefully I'm going to try to pay attention to some of the syncing issues that I've had here. So if the video has to pause while the computer still syncs, hopefully we'll be okay on that. But taking a look at her actual position function. So there's actually two ways that you can find that. And so one way, actually, let me do the thing that always makes you guys mad. I'm going to shrink this down a little bit to get it out of my way. All right, so let's take a look at the actual position function. All right, method one. So method one is going to be the same method that we had done before when we had an initial condition. So we're given that S of 2 equals 12, and we're going to be using that point 212 in order to find C. So we're going to use to find C. So method one is find a general antiderivative. So, and in the problem, we already did that earlier. I have it written above, so I'm just going to bring it down. The general antiderivative was S of t equals my negative 1/3 t cubed plus 3t squared plus t plus c. So that was the general antiderivative that we had from earlier. And then we would just do what we did in the previous set of notes when we were doing the simple finding the specific solution to the differential equation is we're going to use the point 212 to find C. So you would simply plug that in. And so our S of 2 is 12. We would plug 2 in, and that would give us negative 8/3 plus 12 plus 2 plus C. And then we would simply just do the arithmetic for solving for C. And C ends up being equal to 8/3 minus 2, which ends up being 2/3. And so from that, we can then go ahead and write our specific solution or particular solution, depends on what textbook you're using, whether they call it specific or particular, is going to be S of t equal to my negative 1/3 t cubed, 3t squared plus t plus c. And so that's kind of, the idea of kind of relating it to something that we had already done and finding our solution. So just find the general, plug in a point, find the constant, and then write your particular solution. All right, so now what we're going to do is we're going to take a look at a second method where it uses this more idea fundamental theorem of calculus. So method two is to recognize that kind of as we're going through this, we can find the specific value by using the equation that you basically have up here, this relationship where my position at the end is going to be my position at the beginning, quote unquote beginning, which in this case is going to be at 2 seconds, plus the net change. So I'm going to write my S of t as the position at the beginning, which is going to be my S of 2, plus my net change from 2. And now I don't want to find a specific position. I want to find a general all position. So we're going to make this t right here. So your variable here and here needs to match in the problem. And inside of our definite interval is going to be our v of t. And then here's where you get confused. And I almost did it right there. I already used t to be the upper bound variable. I cannot reuse t to be the placeholder variable inside of the definite interval. So, and it doesn't matter what letter you pick for that. I'm just going to pick, I don't know, let's just do x, the x. Because so typically, if you're going to use x for your variable in your upper bound, I put t on the inside. If I'm going to use t for my upper bound, I just stick x on the inside because it's an input anyway. So what this will do is we can find the specific, okay, notice this is the specific particular solution, but doing it in a different way. So coming down through here, we would say, all right, so S of 2 was 12, so we would add that in. And then our net change, okay? Now this right here is going to be the net change in some antiderivative of this v of t or v of x that we have inside of there. So if I want to call, let's call a general antiderivative, just any of them, and usually, like I said, we're going to use c equal to 0. I'm going to call it capital S of t when I do this, right? So, and that's going to be the, not the one I'm looking for, okay? It's a notation thing when we're doing this. I'm calling that little s, and this one I'm calling, the green one's going to be capital S, the little one is little s. They are two different functions. The little s of t is going to be the particular solution that I'm finding, and I'm using capital S of t to represent the general solution that we would have. And I am going to kind of think of this as c equal to 0, because remember that when we do net change, which I'm getting ready to do, the net change does not care about the constant because it's going to cancel out anyway. So when I write that down, it's going to be plus my net change between the ending time, which is going to be t, so it would be capital S of t minus the beginning time s of 2, okay? And your value at 2 is going to, so this is all going to work out to be exactly the same as what we had. We don't have to worry about the plus c because this is a definite interval. It's included inside of these, but it cancels out, so it doesn't really matter what you have there, okay? So when I do this, then we're going to have our 12. The s of t is just an antiderivative. So this s of t is going to be the antiderivative of v of x. So the derivative of that, actually, it's not right there, where s prime of t is going to equal v of t. So it's just an antiderivative. We already had it from before, negative 1/3 t cubed plus 3t squared plus t. Notice that that is the general antiderivative with a constant of 0 in there. Not the one I'm trying to find, the particular one, but just a general one, any one, and it's the easiest one to use. Minus the s of 2 that we had. And again, plugging in that s of 2 would be plugging 2 into this equation. Let me move my little side comment here a little bit out of the way. I'm just going to move it over here. All right, so if I plug 2 into that same general antiderivative that I just wrote down there, I'm going to get the negative 8/3 plus 12 plus 2. And so it's that portion. Now notice, hopefully you'll see that this is giving you a lot of things that are very similar to what we did in the previous example, that this portion right here is going to match this portion down here when we do this. And then I'm going to highlight here in yellow this where I was, and then this part over here. Hopefully you'll notice that that is exactly what I would have had in between here and these items right there. That it's exactly the same thing, just in a different kind of scenario, a little different perspective as we look at it. And so at the very end, this is going to be equal to negative 1/3 t cubed plus 3t squared plus t. And then if you combine everything that's yellow together right there, that's going to end up being the, plus 2/3. And I just realized that this c right here doesn't need to be c. It needs to be the actual 2/3 that we found here. So 2/3, and that ends up being 2/3. So kind of either perspective of how we look at this, whether we find a general antiderivative and plug the point in, or we think of it in this where I am is where I started from plus my net change, that you can come up with two different ways of finding exactly the same thing. All right, so now we're going to go to the summary and we're going to fill that out. All right, so coming in and taking a look at the summary of the important key main facts out of this set of notes. The main important idea is now that our definite integral from A to B, that when we're doing that definite integral, and I'm going to go back to the notation where we just have a generic function inside of the definite integral. Remember that represents that little f of x represents the derivative, that the algebraic way to calculate a definite integral, even though we do know there's a relationship to this area concept, that the algebraic way to calculate that definite integral is going to be to first find an antiderivative. And it doesn't matter which antiderivative you're going to find. Just any antiderivative works. So this is going to be, I'll just put this below, where capital F of x is any antiderivative. And I will say that for our simplistic process that we're going to do, we do typically use c equal to 0, simply because c equal to 0 is the easiest one that's out there. All right, so f of x is any antiderivative. That also means that the derivative of capital F of x is little f of x. And so that is important. Now, obviously, there's something that we have missing here that we have to kind of denote that we're going to do net change. So the notation that's going to happen is we're going to draw that evaluate bar, which we did see when we were using the derivatives. And that evaluate bar is now going to go from A to B. So instead of just plugging in one number, when we draw the evaluate bar and we put a number at the bottom and the top, we're showing that we're going to be calculating a net change. And this is going to be equivalent to f of B minus f of A. The net change, aka displacement, from A to B. And you do want to make sure that you recognize that this is the end and this is the beginning. Just to kind of show you how this works, let's go back to the example that we did previously on the previous page. So if I was calculating the definite integral from 2 to 5 of the velocity function that they gave us, which was negative x squared plus 6x plus 1 dx, that your first step to algebraically do this would be to calculate an antiderivative, and that's where we would have our negative 1/3 x cubed plus 3x squared plus x. Notice that I am not doing the plus c because I'm not doing a general antiderivative. I know that I am evaluating a net change because it's a definite integral. So I show that by putting this evaluate bar from 2 to 5, and then we go ahead and we calculate it. We plug in the 5 first because it's always end minus beginning. So when you plug in the 5 into that, I believe that's where we got our 38 1/3 minus our 11 1/3, which gave us our 27. So do remember it's always end minus beginning when we do that. All right, and then we can take that and we can rearrange that, solve it for capital F of B, and that gives us another relationship that where I end up is where I started plus my net change from on that interval of A to B. And so that's going to give us, just make sure that whatever's in here matches what's there, and that what you're trying to find at the end matches that part right there. All right, so go ahead and start the next problems, complete your understanding, and then come back and watch the homework video.